We know that rotating field alternators, or AC generators, where the field is on the rotor and the output windings form the stator, make up the majority of AC generators in use. There are two types of rotating field AC generator in common use on aircraft. They are brushed AC generators and brushless AC generators. In this lesson, we will look at these two types of AC generator, and we will also examine the various methods used to control frequency in AC generation systems. We will begin by looking at brushed AC generators. The simplest AC generator system is the brushed alternator type. The AC generator itself consists of a rotating field, which is supplied with DC by slip rings and brushes, and a stationary armature, on which are mounted the output windings. In aircraft systems, the output of an AC generator will normally have 3 phases, but for clarity, we only show one phase here. Control of the field excitation current is by the voltage regulator, which samples the generator output and adjusts the excitation current to maintain the correct output voltage, irrespective of the alternator speed and loads. The voltage regulator in its simplest form is a variable resistance, possibly a carbon pile, connected in series with the field coil. The principle of the carbon pile regulator is fully explained in the DC series of lessons. Most modern voltage regulators are electronic devices with no moving parts. The current supply for the excitation of the rotating field is provided initially from the aircraft's DC busbar. This busbar is powered by the battery until the generator is online, so the initial excitation current is supplied by the battery. Once the generator is online, the AC output is fed directly to the voltage regulator, where it is rectified before being used in the field circuit. A brushless AC generator consists of 2 generators. The main generator with a rotating field and an exciter generator with a rotating armature on the same shaft. The purpose of the exciter generator is to provide a current for the main generator rotating field, without the need for slip rings and brushes. Also rotating on the shaft is a rectifier unit. The rotating rectifier converts the AC produced in the exciter armature to DC for the main rotor field. The rectifier unit will normally be a bridge rectifier containing 4 diodes. Rectifiers are fully explained in another lesson. As in the brushed generator system, the voltage regulator samples the main generator output. But in this system, it controls the exciter generator field strength and thereby its output through the rotating rectifier to the main generator field coils. On initial startup, a brushless generator may be self-excited by residual magnetism in the poles of the exciter generator field windings. Or, if the exciter generator field has no residual magnetism, it will be excited by externally supplied DC, possibly from the battery. Because, as their name implies, brushless AC generators have no brushes, they are more reliable than brushed AC generators. And they can also have a higher power-to-weight ratio. Modern brushless AC generators may have a third generator on the same shaft, called a permanent magnet generator, or PMG. This generator provides the excitation current for the exciter generator. The PMG consists of a rotating permanent magnet, which induces a current in its stationary armature windings. The output from the PMG is rectified and fed via the voltage regulator to the stationary field windings of the excitation generator. Irrespective of the type of generator used, the output is usually 115/200 volts, 400 Hz, 3-phase. The frequency of the output of an AC generator will vary directly with the rotational speed of the generator. If an AC generator is driven directly from the engine gearbox, then its speed, and therefore the frequency of its output, will vary directly with engine speed. The output from such a generator is said to be frequency wild. In order for AC generators to be connected in parallel, their output frequencies need to be the same. So frequency wild generators cannot be connected in parallel. The output from a frequency wild AC generator may be used to power an aircraft's electrical de-icing systems, where the resistances that make up the heater mats are not affected by changing frequencies. Inverters can be used to give a constant frequency output from a frequency wild supply. A small number of aircraft types with frequency wild AC generators use a system known as the Variable Speed Constant Frequency System, or VSCF. The frequency wild AC is rectified to DC, which is used to power a static inverter, which then converts the DC to constant frequency AC. If an AC generator can be driven at a constant speed, then the output frequency will be constant. Driving the engine at a constant speed is not usually a practical proposition, so a device is required to keep the speed of the alternator constant, irrespective of the engine speed. The component used to do this is known as a constant speed drive unit, or CSDU. This is often shortened to CSD. The CSDU consists of an engine-driven hydraulic pump, the output of which drives a hydraulic motor, which in turn drives the AC generator. Hydraulic pumps and motors are fully explained in the hydraulic systems lessons. The oil, as well as being the fluid through which the mechanism operates, is also used for lubrication and cooling. It is contained within its own reservoir, entirely separate from the engine oil system. The oil circulates through an oil cooler, which uses ram air, or, on a bypass engine, fan air, as its cooling medium. The output of the hydraulic pump, and therefore the speed of the hydraulic motor, depends on the angle of a swash plate within the pump. The angle of the swash plate is controlled by a speed governor in the generator's load controller. The load controller senses the output frequency of the generator and is responsible for increasing or decreasing the output of the hydraulic pump to vary the torque output of the hydraulic motor to the generator drive in order to maintain a constant frequency output. Most CSDUs are capable of maintaining the alternator output frequency within 5% of 400 Hz. That is, between 380 and 420 Hz, throughout the engine's full RPM range. In the event of a mechanical failure in the generator, the CSDU is protected by a component known as a quill drive. This has a weak link, which will break before any major damage can be caused. Some constant frequency generators have their CSDU and generator combined in one unit, called an integrated drive unit, IDU, or integrated drive generator, IDG. There are a number of indicators on the flight deck to warn the crew of possible CSDU faults. The two main ones are low oil pressure and high oil temperature warning lights. There may also be a CSDU oil temperature indicator. The low oil pressure light will illuminate if the CSDU oil pressure drops below a predetermined minimum value. The high oil temperature light is controlled by a sensor, which is monitoring the CSDU oil outlet temperature. It will illuminate if the oil temperature becomes excessive. If either warning light illuminates, or the oil temperature on the gauge reaches the red arc, then the emergency checklist will normally call for the CSDU to be disconnected. In the event of a malfunction in the CSDU or the alternator, the engine input drive to the CSDU can be disconnected. This will allow both the drive unit and the generator to become stationary. Shown here is a simplified diagram of the drive disconnect mechanism. The disconnect unit is operated by the selection of a momentary action drive disconnect switch by a flight crew member. This operates a solenoid, which causes a mechanical separation of the input drive from the engine to the constant speed unit. The mechanism requires the unit to be rotating for it to operate, so a disconnect should only be attempted when the engine is running. Reconnection may only be done manually on the ground, following shutdown of the engine. There is a great deal of heat generated in a generator's stator windings due to the current flow through them, and some form of cooling system is required. Frequency while generators, or constant frequency generators with separate constant speed drive units, typically use ram air cooling in flight, and some means, such as a mechanical impeller, to induce airflow on the ground. Integrated drive generators use the oil from the speed control system to cool the stators. The oil is cooled in its own oil cooler. That is the end of the lesson. Here is a summary of the main points you should take from it. There are two types of rotating field AC generator in common use on aircraft. They are brushed AC generators and brushless AC generators. A brushless AC generator consists of two generators, the main generator and an exciter generator, on the same shaft. A permanent magnet generator may be used to provide the excitation current for the exciter generator. The frequency of a frequency-wild AC generator varies with engine speed. A hydromechanical CSDU keeps the generator speed constant, irrespective of engine speed. The engine input drive to the CSDU can be disconnected. This will allow both the constant speed drive unit and the generator to become stationary. If the CSDU oil pressure becomes excessively low, or the oil temperature excessively high, the CSDU should be disconnected from the engine drive. Constant frequency AC generators normally have an output of 115/200 volts, 400 Hz, 3-phase.